Okay, thank you. Our next speaker is going to talk about easy parametricity. Looking forward to that. Genoa, please go ahead.
Hi. Okay, so I am going to talk about easy parametricity, and hopefully the talk lives up to the title. So roughly, I'm just going to go over sort of what parametricity is and sort of what I mean by this for anyone who's not come across that. I'm doing an axiom-based approach. So I'm going to talk about models a bit briefly in particular. Hopefully that gives a bit more of a mental picture of what we're actually doing. And then I'm going to sort of state them in them. And I want to show more of a technique than like an actual proof. And I figured the best way to do that was to actually show the proof instead of just show the theorems. So I'm going to do that. And then I've got a couple of like notes and caveats and a couple of exercises at the end. So if we have some family of types, which is defined, some family of functions, which is defined, say, parameterized in a type, and if this is done in like a nice uniform way, say without case analysis, then usually in practice, there's a corresponding equation which says it's well behaved. So if we say had a family of things which are type-like projections, then, you know, unless we do some sort of like case analysis on X, then they're probably going to actually be projections. And similarly, if we have something of this type, then it's probably going to be natural. It's probably going to be iterative function composition. These are also like the church numerals and stuff that you see in like system F and so on. And what we're going to do is we're going to look at what happens, what conditions we can put on the universe to ensure that these hold and that generalizations of these hold. And to do that, we're going to use an axiom. And this is the axiom. So this sort of idea came up a couple of times yesterday. If we have, we write A per B, if all of the maps in B to A are constant, it's easiest to state that as an equivalence. And then we just say that all of the maps from the universe to any U small type, all of those functions are constant. And so what we're going to be doing is we're going to be making a bunch of maps from the universe to useful types and using that to derive equations. There's a few ways of thinking about this one. One of them is that sort of from like classical relational parametricity or what have you, you would hope that we have this sort of this map be natural, that all of the sort of like all of these are natural. If we have we can like state it as a couple of like orthogonality conditions, either just the same as that, or the universe is orthogonal to the type family of the universe, or that the universe is orthogonal to each type in the universe. And there's also a sort of analogy with logical relations, which I'm not really going to go into too much, but this does sort of like link to sort of more classical ideas about parametricity, and in particular, sort of using the universe like a bridge type from those type theories where we have we obtain parametricity from some bridges. So this is our axiom, and this axiom gives us this theorem. So if we have the axiom, if we have a complete univalent category and any low-key small category, then we get these lovely results. So we have that if we have a couple of functors and an unnatural transformation between them, then it's natural. We have if we have a couple of bifunctors and an binatural transformation between them, then it's dinatural. And if we have something that looks like a function, a sort of functor, but we don't really know if it's actually preserves composition yet, then it does. So this is quite useful, you know, if I want to prove something in category theory, and you know, I have this messy naturality condition. I don't anymore. Brilliant. Talking about models of it, because any good axiom should have models. Most of the models we'll get come from having this sort of modality. We're not going to use the modalities sort of later in the talk, but it is where the models come from, and we can sort of restate things in terms of the modalities we want to. So if we have the universe and we have these idempotent monadic modalities, we can state this internally in type theory. We don't need like extra context like this type theory or whatever. Then we take the reflective subuniverse, and under this fairly mild non-triviality condition, I just have to be really small, then we get the parametricity axiom holds in the universe of modal types, which instantly gives us a lot of universes which will have them. They might not be very good universes, though. They might fail to have HITs, or if I is just a two-element type, then we're just going to get the universe of propositions, which isn't very good for studying. Fortunately, in general, we do get that most of the models do in fact have this subuniverse have high inductive types. I thought that it held always, but then I couldn't find a reference. So I don't know if anyone in the audience knows if this is a theorem or not. But it probably is. But regardless, in the models that we're looking at here, there's sort of three groups of them. We do still have that these are closed under appropriate high inductive types. So we sort of have this like univalent version where we have some completion types and subuniverse of discrete types satisfies the parametricity axiom. Which, you know, there's a lot of examples in completion type theory and so on. We can get a fair few of those. If we go in the one-tolerance land, then we have a very similar situation, which is actually quite convenient because we can write that down without sort of extending the theory at all. If I have a universe of sets, I can then take like the category of cubical sets, and then I can interpret type theory in that, and I get parametricity sort of free. And then we also have these two models in assemblies, and cubical assemblies, which also satisfy the parametricity axiom, which means that we can do nice things when we have in predictive universes. So going back to the theorem, we're not going to quite prove this, we're actually going to prove a stronger version. And we're also going to break it up a bit so that hopefully the proof's a bit easier to follow than if I just did this directly. And first, to talk about that, we're going to talk about factorizations in categories. Like the collection of factorizations of some morphism is what you'd expect. You say, well, it's a pair of composable morphisms, which composes to the morphism that we have. And we're going to use this a fair bit in our proofs, and in particular, we're going to use these factorizations here, where one of them is just F and yours id, which are, you can write them down, and they're confusing. And so with that concept, with factorizations, then we can improve the theorem. So before we just had, if we have the complete univalent category D locally small, then we get these conditions. Now we sort of have this intermediate condition. If it's complete and univalent, then it has, this condition here that says that, well, earlier we said that the universe to A, or universe purpose A, here now we're saying it's like a factorization is purpose A. And so we're sort of going to bootstrap ourselves from having the universe to having the type of factorizations. These limits are, in particular, I'll get into what they are momentarily. They are directed, they are subfinite. Classically, all categories have them, they're sort of quite a minor condition. And then we're going to say that if we do have this tameless condition, then in fact the A, B, and C from a couple of slides ago, each of those hold. So in particular, the same for fours and mediate qualities, these two, but, you know, sort of broken it down a bit. And now we're going to prove these, starting with the second one. And the idea for this is quite simple. So here's where we bring in the factorizations. So the identity that we prove, we're going to find some function such that the identity simply becomes of this form, where we have some map from factorizations to morphisms. And if we plug in F then id, or plug in id then F, we should get the same thing. And we want to show that, but we both get the same thing because this is in U by D being locally U small and by B, C being perp to all of the U small types. That means that this map is necessarily constant. And so in particular, we're going to have that these two things are equal. Right. So we just need to do B1 for this half of the theorem. And isn't that hard? So what we need to do sort of for the first case, I can go through the other couple of cases sort of at the end, but the idea is quite similar. Is that we want to show this naturality square. So we have the alpha, then G of F, or we have the F of F and then alpha. These should be equal. And we're going to have some factorization, and we want that in the case that the factorization we provided is this, it should become the top circle, and in the case of factorization is this, it should become the bottom circle. And we can do this. We can say that sort of, well, we take F of the left part, we do alpha, then G of the right part. And in the case the left part's id and the right part's F, we get the top half. And in the case the left part's F, the right half's id, we get the bottom half. And so And so we're done. We've shown that this, or at least the case with Y, because we turn the identity to that form, and then we know that equations of that form actually hold. Brilliant. Then for the proof of the other, oh, I'm going too fast. We have the proof of the other half of the theorem as well. And so for this, we want to say that, well, we want to show that we have this property here, that all maps from the type of factorizations to A are constant. And to do that, we say, well, all maps from U to A are constant. And so we sort of can lift that. If we have a map from U to factorizations, then we will get that it's constant. In particular, if we have just some factorization, we want to show that that this map for the factorizations to A is constant. So if we have some factorization, M of F then H is the same as M of A then H after that. And we can do that just by adjusting, just by composing slightly with, once we have this, we can say we have M from the factorizations. In particular, we can plug these in. And when we plug in 0, so F then id, we then get this. And when we plug in id then F, so 1, we get this. And so now we just need to show that this F actually exists analogously. And we do that by using a particular sort of limit. Now let's fix the morphism, and let's suppose that we have C and that we have, so I go to C as univalent and that we have C. We're going to use some Y pullbacks indexed by propositions. So in detail, oh no, that's the next slide. So we want to interpolate between these. These are qualities we want, because then we can like actually apply stuff, but it's sufficient because C is univalent to just have these isomorphisms. And so we just want to basically solve this equation where we find something to plug into the middle, where when we specialize to the top, there's an isomorphism, and when we specialize to the bottom, there's this other isomorphism. And we do that with these Y pullbacks. So when we have some S, let S join 1, we the result of like just adjoining a terminal object to S. And so on the board, I've got examples for when we have 0, when S is 0, when S is 1, when S is 2. And in particular, we'll use these ones, and this is more familiar, which is useful. Now we can take the wide pullback of that many copies of F. So for 0, we just get the terminal object of S. When it's 1, we just got a single, and when it's 2, we get the ordinary pullback. Then these all have cones from X. So we can take the map from X to Y to just be F, and take the map from X to X to just be id. And because they have cones, we can get a map into the limit. And because we can get a map into the limit, that means that sort of this composite gives the factorization for any sort of sets that we can plug in, or well, we plug in H props, because if T was infinity groupoid, then this diagram up here wouldn't be a category. So we just plug in H props, and in particular, when it's a H prop, all of these limit shapes are just going to be codirected and subfinite, which is sort of quite tame. And then we have this factorization, and we can see that in the case of 0, we have the right parts an isomorphism, and when S is 1, we have that these are isomorphisms, so the left parts of the factorization is an isomorphism. Which is what we want when it's 0. The right part's an isomorphism, and when it's 1, the left part's an isomorphism. Which is great. And in particular, so this is homotopy type theory documents. And what I've shown is great and very useful for the land of 1 categories. But maybe it's not so good for infinity categories. Well, we didn't really use the truncation aspects of it. We could just have said that C was like a wild category, which has sort of enough composition and associativity identities and stuff. And in particular, for our purposes, this definition of wild categories are not. And then we can just copy the definition of being perputane verbatim, and we can say that, oh, well, in that case, where it's both locally perputane and locally small, then we have the pentagon approach. There's a lot of examples of categories like this, although you're going to sort of have to write them down one by one, I guess. But you know, the wild category of types, of pointed types, of there are more wild categories as well. But in particular, like, we can use this quite often, and if we just have, and you know, we also have sort of various closure conditions, because if we have this appropriately tamed wild category, then we can actually define the associators, define the pentagon identity, define these higher coherences, or not, maybe not all at once, but enough of them that we have that if we have a look at some category, then it's our category, say, is also satisfies parametricity. Now, this is a homotopy type conference, so very few of you are going to be saying that you're not a homotopy type theorist. But we do still have something to say about without some top, because if our universe isn't univalent, well, that's fine. We never actually assumed that the universe was univalent. And in particular, we do still need the categories to be univalent, but we can get by with a bit of a weaker condition. So this is sort of very reminiscent of the conditional glue types in cubical type theory, or I think it's called verification, in some other cases where we simply ask, that's usually for like the universe, but we can apply it to a category, where we ask that if we have an object and a partial isomorphism, then we can extend then we can get an object isomorphic to A, which sort of extends this sort of partially defined one and is in fact equal to it when this holds. And the sort of idea of this is well, first off, when we have univalence, this is sort of very automatic, because then the equality is only an isomorphism, and all that we really need is we need like to be able to construct these isomorphisms between this, which is given as a limit, and when it's zero, we can construct the isomorphisms. So in particular, we can replace these diagrams where the isomorphisms are identity functions, which is what this lets us do. And so, okay, that's great. So we've shown that. Why did I put my thing? Why did I put the thing? We've shown this. We've shown that if we have, we can further weaken this. We can replace category with like appropriately wild category. We can replace. We can univalent glue types, which is great. And the only condition is sort of, well, I guess what's the catch? And the catch is that if we have, well, we cannot have that this universe that satisfies parametricity contains an object classifier. So we can't have that it's being. So in some sense, the reason that we do in order to construct objects in this universe, U must be predictive. The proof of this is sort of quite simple, which is just we ask if the type is inhabited, and then we get a map from the universe to this U small type, which just asks, are you inhabited? And 1 is inhabited, 0 isn't. These aren't equal. That map isn't constant, so we can't have the parametricity axiom. And this isn't a deal breaker, fortunately, because, or if we, because in terms of models, we can still have, say, that the, in say simplicial type theory, for example, we would still have that the, discrete universe, that the crisp universe of discrete types will satisfy lem if we have like lem, and it will can still have a sort of object classifier and so on. And we similarly can have that the super universe of all simplicial types in that model will still satisfy as a object classifier. And so we sort of have this quite intermediate. If we want to reason about ordinary types, then we can simply say, well, an ordinary hot, we can say, well, let's work in simplicial type theory. Then we can define this subuniverse, and as long as we can write the definitions of whatever we want to in this subuniverse, it'll restrict further to S, which is just the ordinary category of cuboids. And so this enables equations that we have and that we can get from the theorems to also hold for S. And so despite this, it's still convenient and good and useful. And yeah, that's it. I hope everything goes too fast. Thank you.
Okay, so in theorem A, you assume that you have P joint 1 limits
Yes.
for every proposition.
Yes.
But did I understand, if I understood your proof correctly, you take like more general limits. Now you have this S join 1.
We restrict to just the case where like when we plug in S, we just plug in propositions and we don't need more than that. So like when I've demonstrated it for S, which isn't a proposition, just because I hope that makes it easy to understand what the diagram actually is, but we don't actually use J2 because we plug in a truncated a proposition instead.
I see. Okay, thank you.
Other questions? Yes.
Thank you. So at the beginning, you showed that you get dinaturality for free from parametricity, and you use the pi type. So I assume you can also compose these dinaturals, but it's well known that dinaturals don't compose in general. So what's the catch here? Can you explain have some intuition on this?
In this functor, we can write as something which is a dinatural transformation from the universe to itself, which is covariant in this X and this X, and contravariant in this X and this X. And though, like that's the functor that we're saying is dinatural, but also elements of this type take a function and like an ender function on X and give another ender function on X. And the only sort of those which you can define easily in general are just iterates of the ender function, so the identity, f squared, and so on. And in particular, beta must be composition, like n times n, say f to like f to the n for some n.
Thank you. I wonder what's the relationship to relational parametricity. So does relational parametricity imply your axiom or the other way?
So relational parametricity, you can state parametricity axioms either for the internal logic, have an internal statement, or you can have it as sort of a meta theorem. When you state relational parametricity as an internal statement, you will usually have that this holds. The like U per se. I think that depending on the formulation, there's often going to be like a modality in the way. But you can. But I believe that you can still sort of show that if you have sort of like basic relational parametricity, which lets you get stuff like this, like sort of without any extra doohickeys on it, I guess, then you in fact get the parametricity axiom and in fact get all of its consequences.
Is this more complicated formulation equivalent to your simpler one?
Yes, these two are equivalent.
Thanks.
Thank you. It's very interesting. I mean, I would like to remark that parametricity in a way is an expression of the fact that all types are opaque.
and univalence as well. So they're both sort of related to the fact that you cannot look into a type. What I wonder, have you got an idea how to compute this your axiom? I mean, we know now how to compute this univalence, but if I add this axiom PA, is it clear that I can retain canonicity in the type field? Or?
I don't know. I suspect that you may be able to strengthen it sort of like strengthen tuple type theory and sort of specify, well, we don't just have this, but we like actually have something of like this form or something which is more precise. And when we do have, say, simplicial type theory, I think should have canonicity, and you can show that the universe of discrete types satisfies the parametricity axiom. So yes, but you might have to sort of go for a more specific axiom and use some generality.
You hope for because of the models, but something would need to be studied.
Yes, I don't. To my knowledge, you can't just take this and compute with it.
More questions?
Sorry, it's not a question, but response. If I can say something about this, about the relationship with relational parametricity. So the kind of internal parametricity that I worked on, I think that you don't get this for your whole universe, but you can look at this universe as bridge discrete types, which are sort of where the parametricity relation is the path relation. And in that universe, I think this holds. So there's kind of, to me, two orthogonal aspects of parametricity. There's like the preservation of relations kind, and then there's this kind which says something about the universe being big compared to types that are small. It's something about size. So I don't know that. And then we can talk about it.
Okay, maybe it's time for lunch, but let's first thank our speaker. Yeah.